Welcome everyone. Thank you for joining us. Thomas is going to be talking about Vertex tensor categories and C1 cofiniteness. Feel free to start whenever you're ready. Thank you, Tom.
Yeah, hi everybody. Thanks for staying up so late, some of you. So, I think we are all interested in understanding representation theory of vertex algebras, and for me the guiding principle or the things to do are usually, well, first you start with your class of VOAs that you're interested in, and then you want to understand its representation theory. So firstly, what do you do is you fix a category of modules. So that means you put some niceness conditions on modules that you think are good, and then you first of all try to classify all modules of that type. That's surely the thing you usually do first, but then you would like to understand more structure, and also maybe try to understand relations to other categories, etc. And for that, it's more or less essential to know that you have a tensor category structure on it. So it's somehow important. I mean, it's not somehow, it's definitely very important to try to understand in as much generality as possible under what conditions do you have a vertex tensor category structure. And then once you have it, of course, you want to understand more. So then you would like to know what are all the fusion rules. You really want to understand whether the category is rigid. Unfortunately, that's usually quite a difficult problem. And yeah, and then maybe you want to understand relations to other categories, etc. So, I had Jinwei visiting me, Shashank, when was it? Maybe 5 years ago, 6 years ago. You were there at that time. And he explained more about what he did with EG. And I mean, we all were quite unhappy that we can only get a vertex tensor category structure if the VOA is really nice. So really nice meaning it's a C2 cofinite VOA. And in particular, one always had expected that, for example, affine vertex algebras at admissible level, good enough categories admit modules, admit a vertex tensor category structure. And then we slowly discovered one step after the other how we can indeed be more and more efficient with establishing it. And this is what I want to talk about today. So before I start, I wanted to say one more thing. So I'm quite happy because myself and others, so we have made a lot of progress on admissible level affine VOAs on the whole story. And Jinwei asked me to give a lecture series on that. And that lecture series will be in 2 and 3 weeks online. Of course, everything is always online, and it will also be recorded. So maybe, Flo, I will send you a link to all this series, and maybe some of you want to watch a little bit. I want to give an overview of what we know about affine vertex algebras at admissible level, and this lecture today is maybe a kind of a starting point to that, or precursor. Okay, before I start with writing something down, I copied the main result of HLZ of Wang, Lepowski, and Zhang. So they, you know, they have this series of 8 long articles, which they probably publish as a book at some point, where they establish a working theory of vertex tensor categories. And the main theorem is under certain conditions, a category of VOA modules has a tensor category structure, and it has 2 conditions. So the first one is you need universal intertwining operators. So that means your category has to be closed under what you want to be your tensor product. So here I wrote it down. I think we will upload the slides later. It's, yeah, so the first condition you should read as the category needs to be closed under a tensor product, and the tensor product satisfies a universal property as usual, right? That's how you usually define a tensor product. And the second property is that you have associators, you have associativity isomorphisms, and they formulated that not in the way that you have a single associativity isomorphism, but that you have a family of such associativity isomorphisms labeled by the insertion points. And so the statement is, if you apply your intertwining operators in the appropriate different order, so these are these two expressions I wrote down here, then first of all, both these expressions converge, and the associator is then the map that expresses the first expression to the second one. Okay, and now the statement of their theorem is, so that means if you have a this natural family of families, right, parameterized by the insertion points of associators, then this ensures that you have a braided tensor category structure. And then here I wrote down what it means, right? If you have a tensor category, you need to have a left and right action of the unit, so that is given in the obvious way. There's an explicit formula for the braiding. It is the one I wrote down here. Even though the category needs not necessarily to be a ribbon category, there will always be a twist given just by exponentiating the Virasoro zero mode that has the nice property that it satisfies the usual balancing axiom in a ribbon category. And most importantly, it's a tensor category, so we have an associator, and that is just given by taking the associable limit of your insertion points. Okay, so now you have this nice. Oops, I'm sorry. You have this nice theorem, and now you have to ask the question: well, can I mean, do there exist VOAs that satisfy these conditions? And we know very well that the answer is yes. And so let me maybe first recall so the main property we need is Cn cofinite modules, C1 and C2 cofinite modules. So module is Cn cofinite if it is, well, it needs to be lower bounded for this. So positive energy. And it has to have the Cn quotient has to have finite dimension. So where this Cn subspace is the subspace generated by the minus n modes of the VOA acting on the module. Okay, and one thing that has been known for a while is this very nice statement by Ig, telling us that a C2 cofiniteness is good enough for a vertex tensor category. So let me recall this. If we have a VOA, there are always a few technical conditions. So let me just also recall them. We want it to be integer graded by conformal weight. It's in fact positive integer graded. We want the vacuum to generate the top level to be just the vacuum, and we want the VOA to be its own countergradient dual. And then, so these are standard conditions which are usually satisfied. But the important thing is if then the VOA is in addition C2 cofinite, then the category of all modules of this VOAV is a vertex tensor category. And moreover, and if in addition this category of V modules is semi-simple, so our VOA is rational, then this category of V modules is a modular tensor category. Okay, so I think we all know this, and this is really nice. But what's the problem with it is if you look at the moduli space of VOAs. I mean, if you look at the VOAs you can construct, then you very well know that a VOA is very rarely a C2 cofinite. Now, a guiding principle is, if you look at the VOAs that we know, what kind of VOAs do we know? Well, we know affine vertex algebras in particular. So we take our preferred Lie algebra and the corresponding affine VOA. And then we know we can do standard constructions. We can take cohomologies, so to get W algebras. We can take cosets to get some certain subalgebras. We can take orbifolds, or we can do extensions, right? For example, a special affine VOA is just the free boson, the Heisenberg VOA, and then an extension becomes lattice VOA. So lattice VOAs are covered by this, and we can iterate all these constructions. And if we think about it, we don't know, there's no currently known VOA that is not obtained from an affine one via iterated standard construction. And so, and if we just look at the affines ones itself, then how many C2 cofinite affine VOAs do we have? Well, let me just write it down. So at GB, we don't have to restrict to a Lie algebra. Lie superalgebras also give very nice affine vertex algebras. So let G be a simple basic Lie superalgebra. So basic ensures in particular that we have a non-degenerate invariant linear form, so that we can do a nice central extension. So let G be a basic simple superalgebra, and then I denote by LKG the simple affine VOA. Of this Lie superalgebra at level K. So I normalize the bilinear form in the usual way, in the standard way. Then what is known? Then it's known that this affine VOA is C2 cofinite if, well, two cases, either case equals 0, because then the simple affine VOA is just trivial, or G, a Lie algebra, or OSP. So there's a single non-Lie algebra that is in this sense nice. OSP 1 to n, a single family, and K in positive integer. So only these Westomin-Witten models, one should call them, give us C2 cofinite affine VOAs, and then of course also they are already rational. Okay, now one can ask, is there anything else beyond this theorem of EG? And it's not hard to, well, Shashank did this, so one can verify that Fock modules, appropriate categories of Fock modules for the Heisenberg VOA give a vertex tensor category. And this is understandable, right? Because we know the fusion rule of two Fock modules gives a Fock module times Fock module gives us a single Fock module. So this is quite nice. We know how intertwining operators you can construct explicitly, either using High-Shank-Lee's delta operator or using this standard exponential construction. Either one is fine, and so one can simply explicitly check that you have your associator. So it's so this is fine. But now now for me this continued then with this discussion I had with Jinwei, which eventually turned out to be a joint article with EG. So he helped us with that. And it's the following statement. So I will now write down two theorems, and then we can think about it. What was the key property of these two theorems? So G is simple Lie algebra, and K an admissible level for G. So then one can look at the category of ordinary modules. We called it OKG, or maybe OKG ordinary. there's always a clash of notation because the category O also likes to have an O. Anyway, the category of ordinary modules is a subcategory of the category O. It's the subcategory of those modules that are integrable as modules for the horizontal subalgebra. So that means each conformal weight subspace has finite dimension. So then our statement is that this category is a vertex tensor category. And yeah, and in fact, then subsequent work also established rigidity in many cases in fusion rules. So somehow that's good news, but it turns out for all the remaining things, just the existence of the vertex tensor category was the most important ingredient. The rest you somehow got for free using other nice results. Okay, and then Jinwei and Flora met in Yale, right? Flora, and you also discussed. And you were Igor Frankel's student, and Igor Frankel has always been interested a lot in the Virasoro algebra, more generally probably in W algebras. And it's kind of frustrating, right? Because the Virasoro algebra is the simplest VOA that you know. Physicists for sure knew them always very well, but the physics has the advantage that they don't have to prove a theorem necessarily, right? Anyway, there was no theorem except for the minimum models that Virasoro modules have a vertex tensor category. And what's the structure of it? That the fusion rules are as physics predicted, and etc. And the truth is, of course, there's this whole line of research that is enormously interested in W algebras, and they are, I mean, the whole Langlands correspondence in genus 0 is nothing but saying that there are equivalences of tensor categories of modules of W algebras. So this means if you want to take this story seriously in the VOA sense at least, then you have to have established the vertex tensor category for W algebras. And I recall the Virasoro algebra is the W algebra of SL2, so it's the baby case in that setting. Anyway, so so the Virasoro theorem is the following. So the category here is called OC fin. So, and it's the following category. So it's a category of modules of the Virasoro algebra, the universal Virasoro algebra at central charge C. So this is what I mean by Vir C, whose objects are what? Whose objects are of finite length. They have a finite composition series. And what are the composition factors? The composition factors are simple modules and simple quotients of Verma modules, of reducible Verma modules. So let me just write it down and then tell you in words what all this means. So then it follows that this category of finite length modules, this category of finite length modules is a vertex tensor category. So what do we have? So the Virasoro algebra is the W algebra of the affine vertex algebra of SL2. And then that means we have a functor from modules of the SL2 to Virasoro. And in particular, one can take a Verma module of SL2 and under quantum Hamiltonian reduction, it will give you a Verma module of Virasoro. Now if we choose our generic weight label, just in our preferred complex number, the Verma module will simple, and under quantum Hamiltonian reduction, it will reduce to a simple Verma module of the Virasoro algebra. So it turns out the generic Verma module, that means the generic highest weight module of the Virasoro algebra, is already simple. And you only have a tiny set of modules that are reducible. And these are exactly those that you get from quantum Hamiltonian reduction of reducible Verma modules of SL2 against a twisted character. So it turns out Arakawa and Frankel introduced the notion of twisted quantum Hamiltonian reduction, twisted by a spectral flow automorphism. And so it turns out that means the reducible Verma modules of the Virasoro algebra are parameterized by two labels, a highest weight label of SL2 for a reducible Verma module. So that means wait, am I saying that now correctly? No, I'm sorry. I meant in this a highest weight label for a dominant weight label, and then a spectral flow label, which is a co-weight label, so SL2 a weight label again. So they are, in fact, so that means these reducible Verma models of Virasoro are parameterized by a pair of dominant weights of SL2. Okay, so now why does it, what's the heart of these two things? So in both cases, it turns out these categories are precisely the categories of C1 cofinite modules. And so that means I could have written both theorems unified and shorter. Let V be one of these two VOAs. Let OC1 or C, the category of C1 cofinite modules, it is a Vertex tensor category. Okay, and now for an affine vertex algebra, we know what the C1 cofinite modules are, right? Because what's a C1 cofinite module for an affine VOA is exactly a module that has finite dimensional top level, because the C1 quotient is exactly the top level. For the Virasoro algebra, this is already a hard problem. All right. So how do you see the C1 cofiniteness statement? Well, it turns out that the quantum Hamiltonian reduction functor preserves C1 cofiniteness. So this means if the module is coming from a C1 cofinite module, then you know the C1 cofinite. That's already very good. But it turns out you don't get all modules here, but you can, one way to prove C1 cofiniteness for all modules is using a theorem of Miyamoto. And so let me state this next. So now we want to understand, why is this true? So why is all the what's the heart of this? And these two papers, I mean, these two results were the ones that led Jinwei and me to realize how to efficiently formulate everything. So the answer here is, why is this all working? And the answer is that C1 cofiniteness is the key. So that's why the title has the talk has this title. And the reason is that there's a really nice result by Miyamoto. And he proved the nice statement: if we have two C1 cofinite modules, then it follows that their tensor product is also C1 cofinite. Meaning, if you have an intertwining operator of type M, N to something else, say R, and M and N are C1 cofinite, then R must be C1 cofinite as well. I mean, if you have a surjective intertwining operator. Okay. So, and now this is good, but if you remember, for the tensor category, we need two things. We need with any two modules and an intertwine with any three modules M and R and an intertwining operator of M type M and 2R, with M and N in the category, R must be in the category as well. So we need closure. So, and this is what Miyamoto is guaranteeing. And we need associativity. And again, and luckily, this is what C1 cofiniteness is guaranteeing, because it's guaranteeing that the correlation functions are solutions to differential equations with regular singularity. And so that means you can analytically continue the solutions, and that allows you to ensure that as we have associativity. And so then the formula to formalize it, the theorem that's I hope I've formulated in the optimal way. So so we want C to be a category of modules for a given VUA, such that it satisfies a few properties. So what do we need? We need every object in C is C1 cofinite. That's the key property. And then one should consider the other conditions as mild, though they are not necessarily that mild. So what else do we need? We need it to be closed under kernels and co-kernels. We need it to be an abelian category. We also need it to be closed under the contragradient dual. And these mild conditions are in fact a challenge to establish a tensor category. And then we need it to C to be closed under tensor product. And so, and if all these conditions are satisfied, then C is a vertex tensor categories. Okay. So now, yeah, and I like this theorem a lot because one gets a lot out of it. So what do we get out of it? We get many more examples. And we can think about it. So the first theorem here was the result of that the category of ordinary modules of an affine VUA at admissible level is a vertex tensor category. Well, why is that the case? We know that well, the ordinary modules are precisely the C1 cofinite modules, and it's admissible level. So Tomiyuki proved that this category is semi-simple, finite and semi-simple. So this in particular, it's abelian. It's obviously closed under contragradient dual, and closure under tensor product is ensured by Miyamoto's result. So this means this admissible level result is a baby example of this theorem. The Vertex example before is also an example from this, because it follows from the result that this category OC fin that I wrote down there is exactly the category of C1 cofinite, of all C1 cofinite modules, and this category is generically semi-simple, so generically everything is fine, and it's always of finite length, and that's why this theorem holds. Okay, and now going back to the first example, we can think about it again. So we had here the category of ordinary modules of an affine vertex algebra is always C1 cofinite. So, and of course the contragradient dual of an ordinary module, it has the same conformal weight decomposition, is ordinary as well. So that means a closure under contragradient dual is no problem. Closure under tensor product is guaranteed by Miyamoto, so also no problem. The only problem is I forgot finite length. I'm sorry. The only problem is that it's of finite length. It needs to be of finite length. But and now one can think about it. Now one can. So what do we know about universal affine VUAs? We know the only problem that we have is, in fact, is if the level is a positive rational number, if it is an admissible level, then we have infinite length module. But I think even in that case, Jinwei and Robert are working on it. One can go on. But more generally, we can now look at Lie superalgebras. Right? So what do we know at generic level? Well, at generic level, a module is an ordinary module of an affine VOA if and only if it comes from a finite dimensional module of the horizontal subalgebra, right? So now we know so that means if it is an integrable module if it's a Lie algebra. Now, what happens if we turn to Lie superalgebras? Well, Lie superalgebras have much more finite dimensional modules, right? And in particular, also the category of finite dimensional modules is not semi-simple at all, right? It's usually quite complicated. But finite dimensional modules have one advantage: they must be of finite length, right? Because an infinite length extension must be infinite dimensional. So this means and what holds also for a Lie superalgebra? Generically, the category of modules, ordinary modules, is equivalent to the category of modules of the finite dimensional Lie superalgebra. So one immediate consequence of this theorem is that actually we have vertex tensor category for affine superalgebras generically. And if you work hard, which somebody should do, you also should be able to make lots of statements about non-generic levels, about non-generic levels for superalgebras. Anyway, let me just write down a few well-established further examples. So one of them is the nicest Lie superalgebra in many respects is GL1/1, and it turns out the universal and affine VOA is already simple, and it's independent of the level as long as level is non-zero, and it turns out this is a really nice vertex algebra because one can completely study its category. From the previous theorem, we get the existence of tensor category for free, but then one can also compute all fusion rules and use a KZ equation to establish rigidity. So this is really nice. And then a somehow related example is all the singlet VOAs. Right? You probably all have heard about the triplet VOAs. This is a nice example of C2 cofinite but non-rational VOAs associated to Virasoro algebra in some sense. These triplet VOAs are large extensions of singlet VOAs, and these singlet VOAs in some respects are more fundamental. Anyway, they also one can also establish this tensor category and study it completely. So these two things have been done by Robert, Jinwei, and myself. In fact, most of the things I present have been collaboration with these two. Okay, and then it turns out one can also make statements about many non-generic levels, but also non-admissible levels. So somehow the hierarchy is, well, generic level is generic. This is just what it is. Admissible level is quite nice, but also very interesting and challenging. And the most challenging thing is actually non-generic but non-admissible, because they are already understanding the abelian categories of modules for the affine VOAs is almost nowhere done, just because it's because one is lacking technology. It's okay. So up to now, I wanted to say. What I want to say is you should keep this in mind if you are interested in establishing tensor category. Then you should look for a category of C1 cofinite modules. Okay, now I want to say one more thing, namely, so I wanted to say two things in my talk, namely, that C1 cofiniteness is key to have a good tensor category result. And now I want to continue and tell you one thing you can do if you want to go beyond C1 cofinite modules. So, and again, affine vertex algebras are a guiding principle. And this is what I want to explain in these lectures I'll give in the next two weeks or so on admissible level affine VOAs. So let's think about it. Just when we only take SL2. So what do we have? We know that any module of the finite dimensional Lie algebra of SL2 induces to a module of the universal affine VOA. And now, what does a finite SL2 have? It has, of course, its finite dimensional modules, one simple one for each dimension, but it also has modules that are highest but not lowest weight and the other way around. They are already infinite dimensional. More generally, it has modules that have neither a highest or lowest weight, right? And this is what the physicists call relaxed highest weight modules. One better just calls it weight modules because they have a weight space decomposition. So this and all these weight modules induce to modules of the universal affine VOA, and it turns out at admissible level, not all of them, but at least a huge set of them also are also modules for the simple quotient for the admissible level simple affine VOA. So this means you have many lower bounded modules that are not C1 cofinite. Even worse, if you compute the fusion product of two such modules, you will learn, if you're very good, so David did that, that you in the fusion product modules appear that are not lower bounded. But you will realize that they are related to lower bounded modules via spectral float. Anyway, so what we have there here is we have a category that we should consider as interesting because it is SL2. In fact, we should take any simple Lie algebra as interesting. Admissible level after integer level is the second nicest case, so that should also be considered to be interesting. And we have the problem that almost no module is C1 cofinite. In fact, almost no module is lower bounded. So what can we possibly do? And this is the answer is we can do something. So so the idea is simply what could happen is your VOA could have a sub VOA that has nice C1 cofiniteness properties, and it has a nice and so that means you can study tensor categories nicely there, and then you just use VOA extensions. Now this can, in this situation, this can only happen if this is an infinite order extension. So, so the idea is use infinite order extensions of C1 cofinite cases. Again, now what is the simplest VOA that we know that has these weight modules, this formerly called relaxed highest weight modules? It's the beta gamma VOA. And Robert Allen and Simon Wood, they established, they completely understood the tensor category of those at some point, but it was all complicated. And there's we can get it in fact now for free, absolutely for free. So it turns out you take a beta gamma system and a BC system, a pair of beta gammas and a pair of fermions B and C. Then you take the GL1 invariant, so you have a GL1 and the corresponding orbifold is generated just by the bilinears beta gamma B and BC, beta C and B gamma, these four fields, and the OPE of these fields is the one of GL1/1. That's very easy to check, and in fact, one can show that I forgot who did it, but probably I think this was done in the archetype paper with David. That this orbifold is exactly GL1/1. Conversely, this means that these beta gamma times the fermions is nothing but an infinite sum of GL11 modules. And these here are all simple currents for G1/1. So that these are simple currents. It's not that important here. Important is the VOA of interest times something trivial, right? Free fermions have trivial representation category. It is an extension of something known, and from that you immediately get the tensor category of beta gamma. And because of this infinite extension, it turns out, even though every summand in this, so this means every beta gamma times BC module is an infinite sum of GL1/1 modules, every summand is lower bounded, but the whole sum is not. Okay. And so so this is so, and then it follows that this beta gamma times BC is its category is a vertex tensor category, and then the same holds for the first factor. So this is really nice, and it's even nicer because the complete structure of the category is inherited from GL1/1. So and this is a very nice strategy. So let me give you a few more examples. So it turns out there are these algebras that they have gained some prominence because they constantly appeared in four-dimensional gauge theories, these BP algebras. And what they are is they are certain subregular W algebras of type A. And these SP algebras are their Feigin-Semikhardlov dual algebras, which are principal W algebras of type SLN/1, SLP -1, 1. And it turns out these are extensions of the singlet VOA times times a Heisenberg VOA, and so one also gets nice vertex tensor category structure. So this super algebra doesn't have this C1 deficiency, but the BP algebras have. And so then it follows that one has a vertex tensor category plus all the additional structure. We're actually writing a paper on it, which will appear soon, depending. Okay, and then now the complaint about all this at the moment is, 1 second. The complaint about this is surely that these are isolated examples, right? Because you would like to have not a tensor category for, well, beta gamma is nice, and of course a subregular W algebra is nice, but you would like to have it not for isolated examples, but for the whole families. And let me write down one more example, which is really the example I have been interested in for at least the last 9 years. I really wanted this result, so it's so what is it? The affine VOA of SL2 times a pair of free fermion is an extension. So this statement is called Kazama-Suzuki duality, and physicists knew it since the 80s, and it's very easy to prove. So it's an extension of a principal W algebra of SL2/1 of a super algebra times a Heisenberg, where the levels are related via this formula. So and the principal W algebra of SL2/1 has another name, n equals 2 super Virasova algebra. Under that name, we know that much better. And this example is in fact also a very first example of all the dualities that Andy and I studied. And it's one of the reasons why I think these dualities are quite important. So what do we have here? We have an affine vertex algebra, SL2, and it has the problem that it has all these non-C1 cofinite modules. It has all these not lower bounded modules. It has these modules that have infinite dimensional conformal weight spaces. That's not good. What about the super algebra? Well, it's strongly generated by a Virasoro field. Virasoro field will never be responsible for something not lower bounded. A Heisenberg, also no problem. And then it has two odd fields of conformal weight, 3/2. What's the advantage of an odd field? It squares to 0 in this case. So that means that means simply there is no room for modules that are not lower bounded and for for modules that have infinite dimensional conformal weight spaces. This means every module of the superalgebra is automatically ordinary. That means every module has a chance to be C1 cofinite. And now here, and now there are two papers coming, which are really the ones I wanted. So the first one is the following. It says that if K is admissible, then it follows that that the carry of all relevant modules, so the carry we call the carry of finitely generated weight modules, is of finite length. And we give a complete classification of modules. So this, it's really done. I hope it appears soon. Tomiyuki wants to write something about quantum groups. That's all that is missing. And one consequence of this is this duality is so good that that the same result holds for the superalgebra. These correspondence are so good that you get blockwise equivalences of tensor categories. So in particular, if a block on one side is finite length, then the same as on the other one, and you can get every block at in some way. So and then I noticed that. So Dražen wrote a super nice paper 5 years ago where he realized SL2 and others inside Virasoro and a free field, something like a free field algebra, and that has been quite good. And I noticed that that result can be used to prove C1 cofiniteness for the so that's the other theorem. It's a few-page computation using let's call it the Adamovich trick. It's really nice. This. And these two theorems together imply that we have a vertex tensor carry on the superalgebra, and then via duality also on the carry of admissible level SL2 weight modules. Okay. So so this is so I wanted to say two things in this talk. I wanted to say that C1 cofiniteness is the key criterion to get tensor category in many cases. And if you're looking at a category of modules of a VOA that is not C1 cofinite, then maybe a good strategy is to look for some kind of duality to a superalgebra, because superalgebra have nicer finiteness conditions in this sense, and try to establish it there and then use the duality. And it turns out a lot of things are promising and should generalize well. A lot of things will also be much harder than here in this SL2 case. But in any case, if anybody is interested in it, I will give this lectures, and in particular, I will spend quite a bit on time explaining how this first theorem works. So there are 3-4 nice techniques that get in there, and they're probably quite useful. And then the C1 cofiniteness thing is really just technical computation once we have the good idea. But the point is, so that the news is good in two ways, because there is now a tensor caddy on SL2. So this is really nice, even on all these weight modules and their spectrally flown images and etc. And the other good news is that there is room for generalization, because there's all this zoo of dualities between W algebras and super algebras. But the difficult news is, in this case, the correspondence between the categories is very, very nice and explicit. It will be more complicated in higher rank, and even worse, proving the C1 cofiniteness results. The technique I use won't generalize well, so one has to go to other techniques. But they are there. One just has to work on those. Good. Thanks for your
Thank you so much. Thomas, let me stop the recording and then we'll start with questions.